Now let's have our problem number 3. Okay. So the path of an Earth around the Sun is an ellipse with the Sun at one focus. So the ellipse has a major axis of 186,000 miles, eccentricity of 0.927. So find the distance between the Earth and the Sun. So when the Earth is closest to the Sun and farthest from the Sun. So the part of Earth around the Sun is an ellipse with the Sun at one focus. Okay, it means that the Earth is on the ellipse itself, because the path of the Earth is, or let us consider the Earth as a point within the ellipse. Okay, now since we are not yet in differential calculus, so we will use the formulas in our ellipse in solving the nearest and farthest point of Earth from the Sun. Now, let us consider an ellipse. So according to the problem, the Earth is, of course, has a path. So this will be the elliptical path of the Earth. So let's call this as our Earth. So any point in our ellipse. So within any point of the ellipse, this is our Earth, because this is the path of our Earth. And we would consider one focus, or one of the foci of the Earth, or of the path of the Earth, as the Sun, which is, the Sun is our constant point. So let's say this here, I will put the Sun here. Okay, let's call this as our F1. Take note, I can also put the Sun here, F2, but according to the problem, only one focus, and also there is only one Sun. If this is the focus, this means that this will not move. Okay, the Earth will only revolve around him. So from here, you would notice that the Earth will revolve around its axis until the Earth will be here at this point. Okay, Earth 2. From this observation, okay, we can say that the farthest from the Sun is from F1, or from the Sun, to this part of our major axis, and the closest from the Sun is from this point, or from this negative vertex, to our F1. Okay, now knowing that idea, so, and also the given, which is our major axis is equal to 186 times 10 raised to 6 miles. Okay, now from this we can easily solve the distance, this distance. But how? Now notice that from center to positive V1, or positive vertex, is our A, and from vertex, as I have said, to our center is our C. Consider the length of this, right? So let's say we may have for our letter B, farthest from the sun, B by just simply adding our A plus C. So D F S. Fs means farthest from the sun. Okay, is equal to length C plus A. But what is our A? Note that our major length of our major axis is equal to 2A, in which the length of our major axis is equal to 186 times 10 raised to 6 miles, which is equal to our 2A. So if you would divide both sides by 2, we can have for our A, for A is equal to 93 times 10 raised to 6 miles. Now, how will you get for C then? So solving for C, we have our C, which is unknown yet, but we have our eccentricity. Our E is equal to C over A. So therefore, knowing that our E is equal to 0.927, and our C is unknown, and our E is equal to 93 times 10 raised to 6 miles, our C will be equal to 0.927 times 93 times 10 raised to 6. We have 86.211 times 10 raised to 6 miles, meaning this distance to from the center is 86.211 times 10 raised to 6. That is our C, and our A is 93 times 10 raised to 6. So if you would add this together, so we have DFS is equal to 93 plus 86.211 times 10 raised to 6 miles is equal to 179.211 times 10 raised to 6 miles. Okay, that would be for our letter B. Now, what would be our letter C? Our letter A, I should say. So when the earth is closest to the sun, so closest, we can use our major axis. So DCS, we have our major axis or length of our major axis less DFS, or the distance farthest from the sun, which was solved earlier as 179.211 times 10 raised to 6. So we have our LMS, Lmaxis, or our length max axis, or LM of our axis. We have our length of our major axis. We have 186 times 6 times 10 raised to 6 miles. So we have 186 minus 179.211 times 10 raised to 6 miles. We'll have an answer equal to, so I will just put here my calculator. So minus 186 times 10 raised to 6. So we have 6.789 times 10 raised to 6 miles. This is our TCS. Okay. This is our problem number 2.